Hello and welcome to this revision session for AQA A-Level Physics Paper 1 on the topic of particles and radiation. So if we're successful and we learn in this revision session, we should be able to answer examination questions for A-Level Physics Paper 1 on the particles and radiation topic. So if we've been successful and we've learnt in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for our A-Level Physics in the particles and radiation topic. So how should you prepare for this revision session? Well, when you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show your full working out. Whilst on the right hand side, write down any bits of information which you find useful, any hints and tips on answering questions from this revision session. At the end of this revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising your A-Level Physics? The first step is to learn the key facts. So use the revision guides, class workbook, student prep notes and the textbook to learn the key ideas of the course. You might wish to make mind maps or write out notes yourself. The second step is to test yourself. So use the Caboodle e-learning platform, the Seneca e-learning platform, student knowledge checkers to quickly test your own knowledge. And you may wish to do this from your own cue cards. The third step is to practice examination questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. And you may wish to download your own examination past papers to do this. So the three steps of learn the key facts, testing yourself, and then practicing examination questions are how you should be revising for your A-Level Physics. Now in this revision session, there'll be three types of questions. The first type are general check questions. These are basic questions designed to probe your understanding of the key concepts of the topic. The second are the checkpoint questions. These are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. And the final ones are the assessment point questions. These are past paper examination questions which will mimic the type of questions found in public examinations. So let's now have a look at some questions for particles. So the first question says, calculate the energy of a photon of frequency 4.0 times 10 to the 18 Hz. The microwave region of the electromagnetic spectrum is considered to have wavelengths ranging from 5 millimeters to 50 centimeters. Calculate the range of microwave photons. And then in a microwave oven, photons of energy 1.02 times 10 to the minus 5 eV are used to heat food. Express 1.02 times 10 to the minus 5 eV in joules. Calculate the frequency of the photons and calculate the wavelength of the photons. So pause the video now, then unpause the video when you want to go through your answer. Right, we've got to remember that the equation to work out the energy of the photon is E equals hf, where h is Planck's constant, which is 6.63 times 10 to the minus 34, so we get 2.7 times 10 to the minus 15 joules. The other way to work out the energy of a photon is to say E equals hc over lambda, where c is the speed of light, or 3 times 10 to the 8. Pop in all the values and you get it from 4 times 10 to the minus 23 joules to 4 times 10 to the minus 25 joules. Remember, you convert 5 millimeters into meters and 50 centimeters into meters as well. Now the conversion factor from EV into joules is multiplying by 1.60 times 10 to the minus 19. Again, you are given that conversion value on your examination sheet. So the value will be 1.63 times 10 to the minus 24 joules. We can rearrange our previous equation, say F equals E over H, pop in all the values and we get 2.46 times 10 to the 9 Hz. Then to calculate the wavelength of the photons, again we can use the equation C equals F lambda. That can work for photons as well. So lambda equals C over F, pop the values in and we get 0.12 meters. The next question says, list all of the positive quarks, state the quark combination for the proton and the neutron, compare baryons and mesons, and then what is the antiquark combination of the antineutron. So pause the video now, then unpause the video when you want to go through your answers. Right, you've got to be aware that there's 6 types of quarks and they come in 3 generations. 1 quark from each generation is a positive and 1 quark from each generation is a negative. So the 3 positives are the up, the charmed and the top, with the 3 negatives being the down, the strange and the bottom. Now you've got to remember and memorize the quark combination for the proton and neutron. The proton up up down, the neutron down up down, or dud, because the neutron has no charge. Now if we're comparing baryons and mesons, baryons and mesons are hadrons and are made from quarks, and then baryons have 3 quarks whilst mesons have 1 quark and 1 antiquark pair. Now baryons and mesons, as they're both hadrons, will both experience the strong interaction. Now, what's the antiquark combination of the antineutron? Well, it's the antiquarks of the neutron seen above. So it's anti-down, anti-up, anti-down. The next question says, determine the charge of the following hadrons: the kaon positive and the pion 0, or the neutral pion. Then the second question is, a hadron named Z was discovered in the Large Hadron Collider in Geneva in 2014. It has the quark combination charmed, anti-charmed, down and anti-up. So determine the charge of this particle. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, you've got to remember that you can look on your equation sheet and you'll see what the values of the charge should be for individual quarks. Now remember, the antiquark will have the opposite charge of the quark, and also remember, as well as a hint, because it's K positive, it's going to be a +1, so the quark is +2/3, the anti-strange is +1/3, so it's overall +1. Now remember, particles have to have integer values of charge in this particular unit. Now for the pi 0, it's going to be +2/3 -2/3, so the value is 0. And then here we can see that the charmed has a value of a +2/3, the anti-charmed is a -2/3, the down is -1/3, the anti-up is -2/3, so the overall value is -1. The next question says, figure 30.18 shows another energy level diagram. In this case, energies are given in electron volts. From the list below, state which photon energies could be absorbed by such an atom: 6 eV, 9 eV, 11 eV, 20 eV, 25 eV, 34 eV, or 45 eV. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question, you've got to remember, if there's an energy level difference, then you'll actually get an absorption of a photon. So you'll notice that there are 9 eV, 11 eV, 25 eV, 34 eV, 20 eV, and 45 eV all correspond to differences between energy levels, so they can all be absorbed. But 6 eV does not correspond to any differences between the energy level values, so therefore cannot be absorbed. The next question says, the line spectrum for a particular type of atom is found to include the following wavelengths: 83 nanometers, 50 nanometers, 25 nanometers. For each one, calculate the corresponding photon energies in eV, and then sketch the energy level diagrams which could give rise to these photons. On the diagrams, indicate the corresponding electron transitions responsible for these three spectral lines. So pause the video now, then unpause the video when you want to go through your answers. Right, you've got to remember, to work it out, you will firstly use the equation E equals hc over lambda, because we're given lambda, and we know h and c because they're constants. We convert our nanometers into meters because it's times 10 to the -9, and for each one as well, to go from joules into EV, you divide by 1.6 times 10 to the -19, so you get 15 EV, 25 EV, and 50 EV from the calculation shown on the screen. So what that means is, for your energy transitions, you're going to need a particular diagram which would actually have these different transitions. So you'll need a 50 EV, you will need a 25 EV, and you'll need a 15 EV transition to actually get those particular out. Now again, remember, they're going down because they're being emitted, and emission is when they drop down the levels. The next question says, figure 30.17 shows part of the energy level diagram of an imaginary atom. The arrows represent three transitions between the energy levels. For each of these transitions, calculate the energy of the photon, calculate the frequency and wavelength of the electromagnetic radiation, and then state whether the transition contributed to an absorption or an emission spectrum. So pause the video now, then unpause the video when you want to go through your answer. Right, now again, for each one you can work out the following. So you can say that the energy of the photon is the difference in energy between the energy levels. Now remember, in the diagram you saw before, it's times 10 to the -18 joules, so you just got to use that conversion in there. So if the first one is 5.6 times 10 to the -18 joules, then to work out the frequency, it's this energy divided by h, so you get that one 8.4 times 10 to 15 hertz. Then the wavelength is going to be c over f, so this one's 3.6 times 10 to the -8 meters, and we know it's emission because the electron is dropping down energy levels. You do the same for photon B, and you get 5 times 10 to the -19 joules, 7.5 times 10 to 14 hertz, and 4 times 10 to the -7 meters, with it being emission. Now for photon C, it's 2.2 times 10 to the -18 joules, then to 3.3 times 10 to 15 hertz, and then 9 times 10 to the -8 meters, with it being absorption as the electron goes up the energy levels. The next question says, X-rays are used to find out about the spacings of atomic plates in crystalline materials. Describe how the beams of electrons could be used for the same purpose, and then how might electron diffraction be used to identify a sample of a metal. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one you've got to remember that electrons can behave as waves due to wave-particle duality, so they can be diffracted as a wave would be by the spaces between the atoms. Now each metal will have a different lattice structure, so it'll have a different distance between the atoms, so it'll produce a different diffraction pattern. Now the next question says, a beam of electrons is accelerated from rest through a PD of 1 kilovolt. What is the energy in EV of each electron in the beam? Calculate the speed and then the momentum of each electron. Calculate the de Broglie wavelength of each electron. And would you expect the beam to be significantly diffracted by a metal film in which the atoms are separated by a space of 0.25 times 10 to the minus 9 meters? So pause the video now, then unpause the video when you want to go through your answer. Right, remember in this first one you can convert from kilovolts into EV for electrons because it's an electron volt by just saying it's actually going to be 1000 EV because it'll just work through, so it's 1k EV, because remember an electron which is accelerated through a potential difference of 1 kilovolt will lead to have an energy of having 1 kilo electron volt. Now the next one, we can say that, well, kinetic energy equals a half mv squared. We know what the kinetic energy is from the previous question because we'll just convert that 1 keV into joules. So therefore we can work it through by saying V equals the square root of 2 Ek over m. Pop in all the values. The mass of the electron is given to you on the equation sheet, 9.11 times 10 to the minus 31. So you get 1.9 times 10 to the 7 meters per second. Our momentum is mass times by velocity. We've just worked out the velocity. We know the mass, so it's 1.7 times 10 to the minus 23 kilograms meters per second. Now we know the de Broglie wavelength equation, you're given this in your exam, is lambda equals h over mv. H being the Planck's constant. We've just worked out the momentum, mv, before, so it's 3.9 times 10 to the minus 11 meters. Now that tells you that that's much smaller than 1.25 times 10 to the minus 9 meters. It's out by about a factor of 1, so therefore it's much smaller than the spacing, so there'll only be a small amount of diffraction. Right, the next question says, in 2022, CERN announced the discovery of a new particle known as a pentaquark, which is made of 5 quarks. The table shows the charges on some quarks. The 5 quarks in the pentaquark are C, C, D, S and U. Some scientists say that the pentaquark is made of a meson and a baryon, held together by the attraction of their equal yet opposite charges. Determine the quark combination and the charge of a meson and of a baryon that can make up the pentaquark. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've got to be aware what's a meson. A meson is 1 quark, 1 antiquark, and a baryon is going to be 3 quarks. Now you've got to remember that they're going to have to make an integer value of a charge, okay, and they're going to have to cancel each other through. So what you're going to have to do is, for the meson, it's going to be an anti-charmed, and it's going to be one of the quarks from C, D, S or U to then work it through, to then give out your value there of -1. Then you're going to have 3 quarks from your C, D, S or U. Again, we're going to try and get a combination give us +1, so the 2 will ultimately cancel through. The next question says, a nucleus of rhenium-187 decays to a nucleus of osmonium by emitting a beta particle. Complete the nuclear equation for the decay of rhenium-187, and then the electron released to the decay is 2.6 keV. You may assume that in this case the beta particle receives all the emitted energy. Calculate the speed of the beta minus particle emitted in this decay. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one you've got to remember the beta minus particle is an electron, so it's going to have a value of 0 on the top and -1 on the bottom. Now the numbers on the top have to all add together, so 187 before equals 0 plus 0 plus another value which is 187, and then 75 before equals -1 plus 0 plus another value which is 76. So in this next question, you can convert your energy from keV into joules by using your conversion factor. We can then say that is the kinetic energy. We can then say that therefore equals a half mv squared. So therefore we can work out V, and we get our value to be 3.02 times 10 to the 7 meters per second. Once again, you're given the mass of the electron on the equation sheet. The next question says, pions belong to a group of particles known as mesons. State the quark structure of mesons. Then mesons belong to a family of particles known as leptons. State one property of leptons. Then the charged pions usually decay into a muon and another particle X, as shown by this decay equation. A student suggests that X is an anti-neutrino due to particle conservation laws. Deduce whether the student is correct. So pause the video now, then pause the video when you want to go through your answer. Right, in this first one, it's just knowledge. A meson is a quark and antiquark. Now, you've also got to know the properties of leptons. That's just facts. So, leptons are fundamental. They can't be broken down any further into smaller particles. They've got a non-zero lepton number, so it's either +1 or -1, and a baryon number of 0. You could also say that they'll experience the electromagnetic and weak interaction, but not the strong interaction. Now in this next one, you've got to work out the conservation. So because the charge of the pion minus is going to be -1 and the mu on there is -1, well, it tells the the X value must be 0. The lepton number of the pion is 0, and we know the mu1 has a lepton number of +1, so therefore the X must have a lepton number of -1. And therefore the baryon number of the pion is 0, the baryon number of the muon is 0, so therefore X must have a baryon number of 0. That fits the properties of an antineutrino, so that is correct. The next question says, hadrons are groups of particles. Write a detailed account of hadrons, including how they may be subdivided into other groups of particles, given examples. Then, a high energy interaction between a proton and a pion is shown below. Use conservation laws to show that the interaction is possible. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, you've just got to know lots of key facts about hadrons. So, hadrons are made from quarks. These hadrons and quarks will feel the strong interaction. Hadrons can be split into two groups. That'll be the meson, okay, which are made of 1 quark, 1 antiquark, and baryons, which are made of 3 quarks. The most common type of baryon are the protons and the neutrons. Protons, 2 quarks, so 2 up quarks, 1 down quarks. The neutron, 1 up, 2 down quarks. You'll know that you can work out the overall charge of them, so the proton to be +1 and the neutron to be 0. Mesons will be that 1 quark, 1 antiquark. You can have pions if they don't contain a strange quark, but kaons if they do contain a strange quark. And we're going to have 3 generations of therefore quarks, which are up, down, top, bottom, and charm strange, whilst hadrons have a lepton number of 0, baryons have a baryon number of 1, antibaryons -1, and mesons will be 0. Now in this next one, you've got to show your conservation laws. So you can see that the charge before is +1 and -1, so it's 0 overall, and then afterwards it's 0 +1 -1, so therefore it's 0 afterwards. That is possible. The baryon number 4 is 1 + 0. Then afterwards it's 1 + 0 + 0, so that is conserved. 1 before equals 1 after. And then all the values, all the particles there are not leptons, so they've all got a lepton number of 0. So all 3 are conserved. The next question says, the proton-antiproton collider was a large particle accelerator. An experiment using this proved the existence of a particle called the Z boson. The mass of a Z boson is 91 GeV/c². Show that the mass of the Z boson is nearly 100 times greater than that of the mass of the proton. Protons and an antiproton were accelerated in the particle accelerator to very high energies before they collided. Explain why the protons and antiprotons needed high energies to produce the Z boson. And then Z bosons produced by high energy collisions can have a range of lifetimes. The Z bosons with the longest lifetime are those that will move them very fast. Explain this observation. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to convert our GeV/c² into kilograms. So you do that by converting GeV into joules by doing 10 to the 9, which is giga, times by 1.6 times 10 to the -19. Then you divide it by 3 times 10 to the 8 squared, because it's c squared, so we get 1.62 times 10 to the -25 kilograms. We then divide that by the mass of the proton, 1.67 times 10 to the -25, a value given to you on your examination sheet, so it's 97 times the mass of the proton. Now you need the high energies to do this because we know mass energy is conserved in a particle interaction. So therefore, if we need to create a particle of high mass, we need high energy before that collision to produce it. So therefore, this mass for this larger particle, the Z boson, is coming from the kinetic energy of the colliding particles. Now the particles that have the longest lifetime are those moving very fast, because when you move close to the speed of light, you'll have a relativistic increase in your in the lifetime of it due to the theory of relativity. Now the next question says, ultraviolet light is instant on a zinc plate. if the photon energy is greater than the work function of the zinc, electrons are released. State firstly what is meant by the work function. The ultraviolet section of the electromagnetic spectrum can be split into three parts, known as UVA, UVB, UVC. The range of wavelengths of these parts is given in the table. The minimum de Broglie wavelength of the released electron is 1.50 times 10 to the minus 9 meters. The work function of zinc is 4.30 eV. Deduce whether the UV light incident upon the zinc plate is UVA, UVB or UVC. Then the student used a zinc plate and UV light of different frequencies in an experiment. The student's graph of maximum kinetic energy of the released electrons against the frequency of the incident UV is shown. Einstein's photoelectric equation applies to the situation. Describe two ways that the graph is not consistent with values known for a zinc plate. Your answer should include calculations. So pause the video now, then unpause the video when you want to go through your answer. Firstly, you've just got to memorize what the work function is, and it is the minimum, and that's very important to use the word minimum, the minimum energy required to release electrons from the surface of a metal via the photoelectric effect. Now, which one is it? Well, you can use your equation of saying that lambda equals h over p, which p is the mv, so it's just the de Broglie equation. So we can work out what the momentum is. So it's 4.42 times 10 to the minus 25 kilogram meters per second. We then say, well, momentum is mass times by velocity. So velocity is momentum over mass. So we work that through and we get 4.85 times 10 to the 5 meters per second. We know that kinetic energy is a half mv squared, so we pop the value for v in. We know the mass of an electron, it's given to us on the equation sheet, so it's 1.07 times 10 to the minus 19 joules. That's our kinetic energy of the electron. We then convert the work function into joules by multiplying the value in EV by 1.60 times 10 to the minus 19 joules, okay, and then you work it through, okay, to be 6.88 times 10 to the minus 19 joules. We then say E equals HF plus a half mv squared to work out the total energy of the photon, so we get 7.95 times 10 to the minus 19 joules. Frequency is therefore E over H, so you divide that then by Planck's constant to get 1.20 times 10 to 15 hertz. Finally, we can work out the wavelength by doing lambda equals c over f, where c is the speed of light. So we work it through to be 2.5 times 10 to the minus 7 meters, which is 215 nanometers, which is going to be UVC. Okay, and then finally, on this question, how is it not appropriate? Well, firstly, the y-intercept should be a negative value, and you can see that the y-intercept's about minus 10 eV, much greater than any value that it could be for zinc, given from the previous question. Again, the threshold frequency is your x-intercept, which you can see on the graph to be about 7.5 times 10 to the 14 hertz. It should be about 1 times 10 to 15 hertz if you look at the values given before, so it can't be zinc. And then finally, the gradient of the line should be Planck's constant. It should be 6.63 times 10 to the minus 34. You work it through, and it's actually 2.1 times 10 to the minus 33, so it can't therefore be that particular value. So the next question says, in an experiment to demonstrate the photoelectric effect, ultraviolet light is incident on a metal plate. Photoelectrons are released from the plate with a maximum speed of 3.51 times 10 to the 5 meters per second. Calculate the energy of these photoelectrons in EV. Then the table shows typical values of the work function for 4 different metals. The ultraviolet light used in the experiment has a wavelength of 310 nanometers. Deduce which of the metals was most likely to be used as the metal plate. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one, what you've got to do is you say, right, well, the kinetic energy is a half mv squared, and we know that the mass is that of the electron, which we're given on the equation sheet. So you pop all the values through, and you get the energy in joules to be 5.60 times 10 to the minus 20 joules. You then divide that by 1.6 times 10 to the minus 19 to get the answer to be 0.35 eV. So we can then say, well, the total energy is hc over lambda. We've got lambda, it's 310 times 10 to the minus 9, because nanometers into meters. So we get 6.42 times 10 to the minus 19 joules. So we can then say, well, the overall value of the work function is going to be hf, which we've just worked through, minus the half mv squared, which you know about before. So we convert that 0.35 eV into joules, so it's 5.6 times 10 to the minus 20 joules. We know that the total energy is 6.42 times 10 to the minus 19 joules, so it's 5.86 times 10 to the minus 19 joules, which when you look across must be magnesium. The next question said, photons are only emitted from a given metal surface if the frequency of the instant radiation is above a particular value. Explain why. Then the student makes the following statement. It does not matter what the value of the work function is for a particular metal. Photoelectrons can always be released if the intensity of the instant light is high enough. So criticize the student's statement. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's important to know that in the photoelectric effect that each photon will only interact with one electron at a time, and the electrons absorb energy from the photons, or the photons transfer energy to these electrons. So the minimum energy required for the electron to be emitted is that work function, which actually must be lower than the photon energy transferred to the electron. So the higher photon energy is from the higher frequency, because E equals hf. So when the energy is above the work function, the electron is emitted. Now the statement can't be right below because the intensity of the instant light relates to the number of photons which are hitting the surface per second. So therefore it is related to the number of photoelectrons emitted per second, but the intensity does not affect the energy of the photon, okay, or then the photoelectron emitted. So therefore it doesn't affect whether an electron can overcome that work function and be emitted from the material. The next question says, figure 30.28 shows 5 of the energy levels in a helium ion. The lowest energy level is known as the ground state. Firstly, calculate the energy in joules that's required to completely remove the remaining electron originally in its ground state from the helium ion. Then calculate the frequency of the radiation which is emitted when the electron drops from n equals 3 to n equals 2. State the region of the spectrum in which the radiation lies in, and then without further calculation describe qualitatively how the frequency of radiation emitted when the electron drops from n to 2 compares with that of the radiation emitted when it drops from 3 to 2. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've just got to look at the difference from the ground state up into 0. So therefore it's 54.4 eV. Turn that into joules by multiplying by 1.6 times 10 to the minus 19, and it's 8.7 times 10 to the minus 18 joules. This next one, to see the energy emitted, you've got to find the difference in the two energy levels. So you get 7.5 EV. You can then say F equals E over H. But remember, that's only if E is in joules. So you convert the EV first into joules, divided by Planck's constant, and it's 1.8 times 10 to 15 Hertz, which you should know lies in the ultraviolet region. Then finally, you can see that from the values given that the drop in energy from n equals 2 to n equals 1 is much more than that from 3 to 2, because you can tell from the difference in the energy level values are given in the diagram. So therefore the frequency of the light emitted must be much higher, because the frequency of the radiation links directly to the energy. The next question says, the spectrum of the sun has dark lines. These dark lines are due to the absorption of certain wavelengths by the cooler gases in the atmosphere of the sun. One particular dark spectral line has a wavelength of 510 nanometers. Calculate the energy of a photon with this wavelength. Explain the significance of the energy levels having negative values, and then explain, with reference to the energy level diagram above, how a dark line in the spectrum may be due to the presence of helium in the atmosphere of the sun. Then all the light absorbed by the atoms in the sun's atmosphere is re-emitted. Suggest why a dark spectral line of wavelength 590 nanometers is still observed from the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, the first one you've got to do is use your photon energy equation, but we've already been given the wavelength, E equals hc over lambda, convert nanometers into meters by times 10 to the minus 9, so the value is 3.4 times 10 to the minus 19 joules. It's important to know why they have negative values. It's because we say the electrons have zero potential energy at infinity when they're released from the atom, so therefore they've got to have put energy in to get to zero, so they start off as a negative value. Now you can see that in the next question the electron's excited from the minus 5.8 times 10 to the 19 joules level to the minus 2.4 times 10 to the minus 19 joule level. So it absorbs all that energy level of the instant photon. And then why would it still be observed from the Earth? Because this instant light is then directional and is re-emitted in all directions. The next question says, figure 30.30 shows 3 of the energy levels in an isolated hydrogen atom. The lowest energy level is known as the ground state. Explain what happens to an electron in the ground state when it absorbs energy from a photon energy 21.8 times 10 to the minus 19 joules. Explain why a photon is emitted when an electron makes a transition between energy levels n equals 3 and n equals 2. Calculate the wavelength of electromagnetic radiation emitted when an electron makes a jump between the n equals 3 and n equals 2. And in the diagram, each energy level is labelled with its principal quantum number n. Use the energy level diagram to show that the energy E of an energy level is inversely proportional to n squared. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, well, if it goes from this ground state and it absorbs the energy, well, it's going to actually be completely removed from the nucleus because it'll have enough energy to actually get to the nucleus and then to get to the top of the atom and then leave, so it'll be totally removed from that atom. Now, what's happening is that we know that when it's going downwards, well, then the potential is less than the n equals 2 than 3, so therefore energy must be given out in the form of a photon. That's the principle of line spectra. And then to work out the jump, you work out your change in energy level, so it's going to be 3 eV. Convert that into joules by multiplying by 1.6 times 10 to the minus 19. You then say lambda equals hc over E, work it through to be 4.1 times 10 to the minus 7 meters. And then this next one is just shown about the idea of inverse proportionality. So if E is directly proportional to 1 over n squared, well, therefore E n squared equals a constant. So for each energy level, do E times by n squared. They all come out at approximately the same value, minus 21.6, proving that they're inversely proportional. The next question says, Sirius A is the brightest star in the night sky and is mostly composed of hydrogen. When light from Sirius A passes through the hydrogen in the outer layers of the star, some of the light is absorbed. This causes the electrons in the hydrogen to be excited. The diagram shows an electron being excited from the minus 3.40 eV level to the minus 1.50 eV level. The wavelengths of the different colours of visible light are shown in the table below. Deduce the colour of the visible light that caused the electron transition shown in the diagram. So pause the video now, then unpause the video when you want to go through your answer. So the first thing you do in this question is look at what the difference is in the two energy levels, and it's 1.9 eV. You then multiply by 1.60 times 10 to the minus 19 to get it into joules. 3.0 times 10 to the minus 19 joules. You can then say, well, frequency is E over H, so you divide it by Planck's constant to get the frequency out. We can then say the wavelength is C over F, where C is the speed of light. We can use C because it's a photon, so therefore traveling at the speed of light. So we get the value to be 6.54 times 10 to the minus 7 meters, which is going to be about 654 nanometers, because you can go up by 2 because we're going to minus 9 from minus 7. So therefore the light, when you look at the table, must be red. The next question says, the diagram shows the energy levels for an atom of hydrogen. An electron is in the ground state, minus 13.6 eV level of this atom. A photon interacts with this electron. Explain why this interaction caused the emission of another photon. Then a photon has a wavelength of 280 nanometers. Determine the energy in eV of this photon, then explain whether the atom of hydrogen could emit a photon with this energy. So pause the video now, then unpause the video when you want to go through your answer. Right, it'll cause an emission because we know that the electron is going to move to a higher energy level when it's been absorbed, when it's had energy absorbed into it. Therefore, it will drop back down after it's been excited. When it de-excites and goes back down, it will release a photon. Now in this next one, we know that from the question, we know V equals F lambda. So we know that F is going to be V, which is 3 times 10 to the 8 because it's a photon, divided by the wavelength, which is 218 times 10 to the minus 9 because we go from nanometers to meters. We can then say E equals HF. So we plug in the value of F, which we just worked out, and we can work out our E to be 9.12 times 10 to the minus 19 joules. We then divide by 1.60 times 10 to the minus 19 to get our value in EV, 5.70 EV. Now, could the atom of hydrogen emit a photon with this energy? Well, there's no difference of 5.7 eV in those energy level diagrams of hydrogen, so it's not possible for this photon to be emitted. Now the next question says, explain what is meant by the wave-particle duality of electromagnetic radiation, then explain how the photoelectric effect gives the evidence for this phenomena, then the figure shows the maximum kinetic energy of the emitted photoelectrons as the frequency of the incident radiation on a sodium plate is varied. Explain why there are no photoelectrons emitted when the frequency of the incident light is less than 5.6 times 10 to the 14 Hz. Calculate the work function of sodium and use the graph to calculate the value of Planck's constant in joule seconds. So pause the video now, then unpause the video when you want to go through your answer. Well, the first one is just a definition. The wave-particle duality is the idea that electromagnetic radiation displays both wave-like behavior and particle-like behavior. The photoelectric effect indicates that you can only release radiation, okay, above a certain frequency, the threshold frequency. So, and then at that point, the energy of the photoelectrons will increase with that frequency, indicating that they are receiving the energy in a particular packet, which is a photon, which is when they're exhibiting particle behavior. Now, there are no photons emitted below that frequency because the energy of the photon will be less than the work function, the minimum energy needed for an electron to be emitted from the surface of the metal. So therefore, it won't actually be emitted below that point. The work function, well, we know we can look at the graph, and that on the graph, the threshold frequency is 5.6 times 10 to 14 Hz. Therefore, E equals HF. So we can work out the work function, the energy equivalent of the threshold frequency, by multiplying the frequency by Planck's constant. So we get 3.7 times 10 to the minus 19 joules. And then on this graph, the gradient of the straight line is Planck's constant. So you work out the gradient of the line, and we get 6.6 times 10 to the minus 34 joule seconds. The next question says, the table below shows the work function of four metals. The electromagnetic radiation of wavelength 380 nanometers is incident on all the metals. Photoelectrons are just emitted from metal A. Explain in terms of photons why metal C will not emit photoelectrons. Then calculate the maximum wavelength of the electromagnetic radiation in nanometers that will just eject photoelectrons from metal D, and then metal B is now exposed to the electromagnetic radiation of a different wavelength. The energy of each instant photon is 5.3 eV. Calculate the minimum de Broglie wavelength of the emitted photoelectrons. So pause the video now, then unpause the video when you want to go through your answers. Right, so it won't emit photoelectrons because the energy of the photon is less than the work function. So when you work it out, the energy of doing E equals hc over lambda, and then working it through in joules, then working out the value of it in EV by dividing by 1.6 times 10 to the minus 19, the energy is less than the work function. Now, what's the maximum wavelength? Well, what you'll do is you'll work out to be 190 nanometers, but what you'll do is you'll say, right, well, E equals hc over lambda, so lambda equals hc over E. So the E value is going to be just enough to overcome the work function, so 6.4 eV, which you convert 6.4 eV into joules by doing 6.4 times 1.6 times 10 to the minus 19, so you get 190 nanometers. Now, we can see here that we know that the kinetic energy is going to be the total energy, which is 5.3, minus the work function, which from the table is 4.1, so therefore overall is 1.2 eV. So we can therefore work out what the velocity is going to be by then popping it into the kinetic energy equation. But remember, we convert the 1.2 eV into joules by times it by 1.6 times 10 to the minus 19. So we work it all through, and lambda is 1.1 times 10 to the minus 19 meters. The next question says, pions are created in the upper atmosphere when high-energy cosmic rays interact with nuclei. Pions are mesons and they quickly decay to muons. Muons are leptons with a mass of 106 MeV over c squared. Give the possible quark structure of a pion. Then the equation shows a pion decaying into a muon and an antineutrino. The energy and momentum must be conserved in this decay. Explain two of the conservation laws that will apply to this decay, and then calculate the mass in kilograms of a muon. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, pion can't contain a strange quark because it would therefore be a kaon if it wasn't. You can see what's the structure of a pion. Well, it's got to add up to either an integer of +1, -1 or 0. So you can have the up anti-down up, anti-up, or down, anti-down. Now in this next one, you just got to tot up those conservation laws, and the three you've got to remember are the conservation of charge, the conservation of lepton number, the conservation of baryon number. Now you can see the charges on the top. It's easy, and remember neutrino, neutral, okay, has no charge. The lepton numbers, you've got to remember that if it's a meson, it doesn't have a lepton number. A normal lepton will have a value of +1, and an anti-lepton, such as the anti-neutrino, will have a -1, and none of them are baryons, so they're all 0. This next one, you convert your mass from MeV over C squared into kilograms by multiplying the EV out, the MeV out into joules by doing 10 to the 6 times by 1.6 times 10 to the minus 19. We can then divide it by 3 times 10 to the 8 squared for C squared to get 1.88 times 10 to the minus 28 kilograms. The next question says, describe the interaction that is responsible for keeping protons and neutrons together in a stable nucleus. You should include the details of the properties of the interaction in your answer. Nuclei can decay by alpha decay and beta decay. In alpha decay, only one particle is emitted, but in beta decay, there are 2 emitted particles. Explain how baryon number is conserved in alpha and beta decay. The kaon decays by the weak interaction. The equation shows an example of kaon decay. State one feature of this decay that shows us an example of the weak interaction. And then there have been considerable advances in our understanding of particle physics over the past 100 years. Explain why it is necessary for many teams of scientists and engineers to collaborate in order for these advances to be made. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's due to the strong interaction. That's a fact you've got to remember. Now it's got a short range, or it's got a traction up to 5 femtometers. It's got repulsion up to about a distance of 1 femtometer or below, and it's negligible beyond 5 femtometers. The strong interaction only affects hadrons, or baryons and mesons, or things made from quarks, and is mediated by the pion or the gluon exchange particle. Now in alpha decay, we know that the numbers of neutrons and protons are unchanged because there's 2 protons, 2 neutrons leaving an atomic nucleus, so therefore the baryon number is unchanged. In a beta decay, the neutron changes to a proton. They've both got the same baryon number, so it is conserved, and it will also produce an electron and antineutrino, okay, or the other way around. It'll produce an anti-electron, which is a positron, and a neutrino, and in this instance they will both have 0 baryon numbers, so it can ensure the baryon number is decayed. We know that this decay is an example of the weak interaction because strangeness is not conserved. Strangeness is only conserved in strong interactions, not weak interactions. And finally, we've got to understand for particle physics that the results of the experiments in particle physics have to be independently checked or peer reviewed before they're accepted. Particle accelerators are very expensive, and collaboration helps spread the cost of building them. And then we've got lots of data to process, and we need many skills and disciplines to do this. The next question says, students investigated the photoelectric effect. They used a piece of magnesium ribbon placed inside the cylinder of a copper gauze as shown. There was an air gap between the copper gauze and the magnesium ribbon. The copper gauze was connected to the positive terminal of a power supply. The magnesium ribbon and the sensitive ammeter were connected to the negative terminal of the power supply as shown. The students made the following observations. When the light from an ultraviolet lamp was incident on the gauze and ribbon, a current was detected in the ammeter. When the polarity of the power was reversed, the current decreased to 0. Explain these observations. Then the student reconnected the circuit so that a current was detected when ultraviolet light was incident on the gauze and the ribbon. The students replaced their original light with an ultraviolet lamp with a much greater intensity. Explain the effect this had on the experiment. And then the ultraviolet lamp was replaced by a laser which emitted red light of wavelength 633 nanometers. To deduce whether the photoelectric effect would occur, the work function of magnesium is 3.7 eV. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, you'll notice that the photons of the ultraviolet light will cause the photoelectrons to be emitted from the surface of the magnesium ribbon. Now this occurs because the photon energy of from the ultraviolet light is greater than the work function of the magnesium, because the frequency of the ultraviolet light E equals HF, therefore gives a value of energy greater than the work function, or you could just say the frequency is greater than the threshold frequency of magnesium. Now electrons are always attracted to the positively charged gauze, so therefore will move and create a current. So when the polarity is reversed, the current goes to 0 because the electrons won't have enough kinetic energy to move across the gap, because they're now being repelled by the negative charge on the gauze now, so they'll want to stay on the other side. Now what effect would this have? Well, you'll notice that the photons are already being emitted by the circuit. So a greater intensity will mean there are more photons hitting the surface every second, so therefore there are more electrons being being removed from the metal surface per second, so therefore there's a greater rate of flow of charge, so the value on the ammeter goes up. Now in this next question, we've got the wavelength, so we can work out the frequency of the light by doing F equals c over lambda. C is the speed of light because it's a photon. Therefore, we can work out the frequency. We can say E equals hf, and we work it out to be 3.14 times 10 to the minus 19 joules. So therefore, we can work that out by saying, well, we can look at the work function and put that into joules, and times 3.7 eV by 1.6 times 10 to the minus 19. Compare the two factors. The energy of the photon is less than the work function, so the photoelectric effect will not take place. The next question says, the Planck constant is an important universal constant used in the study of wave-particle duality. In the demonstration of the photoelectric effect, ultraviolet radiation with a frequency of 2.8 times 10 to 16 Hz is instant on the surface of clean zinc. Electrons are released from the surface of zinc. Calculate the maximum velocity of the released electrons. The work function of zinc is 6.9 times 10 to the minus 19 joules. Atomic electrons are confined within the atom. One model of the atomic electron suggests that the wave associated with an atomic electron forms a standing wave that fits in with the diameter d of the atom. The diagram shows the lowest frequency standing wave that fits into the diameter of the atom. Calculate the momentum of the electron with d equals 2.00 times 10 to the minus 10 meters. Then electrons in an atom can only exist at discrete energy levels. Explain how this standing wave model can account for this. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, you can say, what's the kinetic energy? Well, the kinetic energy is going to be equal to the energy of the photon, which is hf. So you've got F in the question, 2.8 times 10 to the 16, times by Planck's constant, minus the work function in joules, which we're given to be 6.9 times 10 to the minus 19. So we've got our kinetic energy. We're going to then say V equals the square root of 2ek over m. Just rearrange the kinetic energy equation. We know the mass of the electron now. We use the mass of the electron because it's the electron's kinetic energy we've got, so therefore it's 6.26 times 10 to the 6 meters per second. This next one, we can work out the momentum because we know the de Broglie wavelength is the Planck's constant over mv, which is the momentum. So we can rearrange it. We can make the momentum the subject, and we get 1.67 times 10 to the minus 24 kilogram meters per second. Now in this last one, how can the standard model account for this? Well, we know with the standing wave, it can only occur in discrete numbers. It can only occur when you've got half wavelengths. So therefore, a discrete number of half wavelengths fit into the diameter of the atom, and therefore they link the energy levels, and that's why you get discrete energy levels, because in standard waves, they can only occur at particular frequencies called harmonics, so they will then convert into the different standard wave values. The next question says, the picture shows an electron diffraction pattern produced by graphite in a cathode ray tube. Describe the experiment that produces this pattern. Draw a labeled diagram of the apparatus to help you. Explain why the light and dark circles as shown in the picture are produced, stating what this evidence provides about electron behavior. A potential difference of 5 keV is used to accelerate the electrons. Calculate the work done on the electrons. Calculate the de Broglie wavelength of the accelerated electrons and suggest a value for the space in between the graphite atoms just to find your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how would you do this experiment? Well, you need to be able to get electrons to the graphite. So you'd have in an evacuated tube where there's no air, the electrons are released by thermionic emission, so you heat up the surface to release electrons by ionization. We then will put them in an area where they will accelerate, so you go through a potential difference, so they're accelerated towards an anode by an electrical field. They then will hit the graphite target and diffract through. Remember, it has to be graphite 1 atom thick to get a nice clear diffraction pattern, and the electrons are then detected on the screen as shown. Now the light and dark circles will provide evidence for the wave nature of the electrons, because the light circles are produced by the electrons diffracting, which is a wave property, and then having constructive interference, so the waves arrive in phase producing a light circle there, and dark circles are caused by destructive interference where the waves from the different electrons arrive out of phase or in antiphase. Now the work done, we can link that into, you're looking at the idea of just converting that into joules. So it's turning kilovolts into joules. So remember, 5 kilovolts gives you an energy of 5 kiloelectron volts because there's electrons being accelerated. So you convert that into joules by multiplying by 1.6 times 10 to the minus 19. So you get 8 times 10 to the minus 16 joules. The de Broglie wavelength is, well, you know what that the work done is a half mv squared. So you can work out what the values that's going to be by doing a half times by mass, which you're given on the equation sheet, times by the velocity squared. Work that through to get v, which is 4.2 times 10 to the 7 meters per second. We're going to say the wavelength for the de Broglie is the Planck's constant over mv. You've got all the other values. You pop in the value of v you've worked through, and it's 1.7 times 10 to the 11 minus 11 meters. Now, for diffraction, the gap size needs to be approximately the same as the de Broglie wavelength, so it should be equal to approximately that value, 1.74 times 10 to the minus 11 meters. The next question says, electrons exhibit wave-like behavior. Calculate the wavelength in meters of an electron with a speed of 2.09 times 10 to the 6 meters per second. Discuss whether the electrons with this wavelength will be diffracted by a thin piece of graphite. And in an electron diffraction experiment, electrons are accelerated at speeds that produce diffraction by a piece of graphite. In an electron diffraction tube, rings are produced on a screen. Describe and explain the effect of decreasing the potential difference through which the electrons are accelerated through on the rings produced. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, we know that the de Broglie wavelength is h over mv. Pop in all the values and we get 3.48 times 10 to the minus 10 meters. Now, would that actually cause diffraction? Well, yes, it would do, because that wavelength is approximately the order as the spacing of that of atoms. You should know it's about 10 to the minus 10 meters, so therefore it would work through. Now, in the next one, if you decrease the potential difference, the momentum of the particles will be less because they've got a lower velocity, so therefore the de Broglie wavelength, lambda equals h over mv. If mv goes down, well then lambda will go up, so therefore the rings will have to have a greater diameter, but because they're more spread out, the brightness will be less. The next question says, the neon lamp shown is a glass-filled bulb with a neon gas at low pressure. When in use, the neon gas between the electrodes emits electromagnetic radiation. Explain why this happens when there's an electrical current between the electrodes. Then when the light from the neon lamp is incident upon a metal surface, the electrons with a maximum speed of 2.68 times 10 to the 5 meters per second are emitted from the surface. The table shows the work function of some metals. Deduce which metal is the light incident upon us, and the frequency of the light is 5.56 times 10 to the 14 hertz. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, how does it work? Well, the electrical current is a movement of the electrons between the electrodes. Those electrons collide with the neon atoms. In that collision, the electrons transfer energy to the neon atoms. That makes the electrons in the neon atoms be excited to higher energy levels. So therefore, after a short time, they'll then de-excite back down to their normal state. When the electrons in that neon then de-excite, that will emit a photon of electromagnetic radiation. Now in this next question, we've got the frequency, so we can work out the photon energy, so E equals hf, and we get E to be 3.69 times 10 to the minus 19 joules. We can know that the kinetic energy is a half mv squared. We've got the idea that it's going to be a half times by the mass of the electron times by the velocity given in the question, so therefore it's 3.27 times 10 to the minus 20 joules. We know that the work function is therefore going to be the photon energy minus this kinetic energy, so we get the work function to be 3.36 times 10 to the minus 19 joules, and looking on the table, that is cesium. So that brings an end to our revision session today. So hopefully, if you've been successful and you've learned in this revision session, you should be able to answer A-level physics examination questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for A-level physics in particles and radiation. So I hope you've enjoyed this revision session on the particles and radiation topic for AQA A-level physics. Thank you so much, and have, as always, a lovely day.